Stephen, Greb, the floor is yours. Thank you for coming.
Well, thank you, Nina. I want to thank Nina, and what a pleasure it is to be here today and participating in this conference. I've already met a lot of fascinating folks and people that are doing some amazing work in this field. So as Nina pointed out this afternoon, we're going to change gears and talk a little bit about water quality. Let me see how I can drive this thing here. Oh, it's already switched gears. So as she has mentioned, I'm Stephen Grubb. I work at the University of Wisconsin in Madison, Wisconsin. I've also been director of GeoAquaWatch, and though recently have stepped down. So Wisconsin is almost exactly due north of here, 3,600 kilometers. So, and besides sharing a passion for water and water quality and trying to protect our water resources, we share with Costa Rica a number of birds. And not to get sidetracked here too much, but these birds, neotropical migrants, are birds that for the most part live here in Costa Rica. And once a year, they fly 3,600 kilometers to my backyard and nest and have their babies, and then they fly back to Costa Rica. So thank you for taking care of them the other 9 months of the year. And we enjoy having them. This Baltimore Oriole, this orange bird here, just showed up Saturday just before I was leaving to come here, ironically. So just to put this talk a little bit in context, some of these facts we've heard over the last day or so. About 1/3 of the world's water resources are in Latin America. Latin America is rich in water resources. And in some countries, the surface water accounts for a majority of the water supply that the country is using. Unfortunately, less than 40% of the wastewater is treated, and about 150 million people, or about a quarter of the Latin American Caribbean population, live in water-scarce areas, and most notably the Central American Dry Corridor. And a number of areas do lack safe sanitation. And exacerbating this, of course, is a number of factors such as climate change, which is disrupting the water cycle, which we've heard about the last few days. Glaciers retreating, watersheds are degrading, of course, due to a number of reasons: pollution from effluent from factories and agricultural use, mining, what have you. And on top of all this, there is a dearth or a lack of water quality information. And I think as someone mentioned yesterday, it's hard for us to make sound decisions or how to manage our water resources without having the necessary information first. A number of you have asked me about Wisconsin, where it is and what happens there. And so I just put in a slide or two of Wisconsin. So we are in the north central part of the United States. We are blessed with a lot of great fresh water. We are bordered on the east side by Lake Michigan, one of the Great Lakes, on the north side by Lake Superior, our deepest Great Lake, and on the west by the Mississippi River. In addition to that, we have over 15,000 inland lakes, and of course, a number of rivers and streams to go with that. Our Department of Natural Resources came to us one year and said, with staffing cuts and our shortages and resources, we're having a hard time keeping track of these lakes or what their water quality conditions are. Can satellite remote sensing help us? So we had launched this project, and now it's gone on for a number of years, but we started using Landsat, and it has since evolved. But we use satellites to monitor our 15,000 lakes because we just don't have staff to go out there and collect samples. So We also employ citizen science, and I haven't heard a lot of talk of that at this meeting yet, but we couldn't do this work without the citizen science folks, the people in the community that live on these lakes that actually are very good, very vigilant about getting out there and collecting samples for us. And we need that kind of information for validation and calibration and validation. And so we create maps like this. This is a map of Secudisc, or water clarity, for the northern part of our state. And you can see is this mosaic of different colors, which vary based on the water clarity of the lake. So I'm just going to do a 1-minute primer. And if you want to hear more about this, you'll come to Saturday's training session. But how we actually measure freshwater quality from satellites. Of course, the sun is our energy source. The energy from the sun coming in from, I guess it's from your right side there, goes into the water. It interacts with material in the water column. And a small portion of this energy comes off the surface. We call this emergent flux. And of course, goes up vertically to where it is intercepted by our satellite remote sensing sensor. There's a lot that goes on here. It's of course it's pretty complex issue. Things like the scattering of the light, the moisture in the air, particulates in the air, a number of things kind of mask the symbol. But basically, we're measuring things in the water column that we call optically active, things like phytoplankton, chlorophyll, algae, suspended solids, turbidity, those kinds of things, plus the color of the water, which can be a measure of the organic matter in the water column. If we look at the water column, from the surface, we look down at the water, we use what we call a spectroradiometer, and we look at the signal, the reflectance off the surface of the water. We see this squiggly line over the course of the visible wavelengths here. So, and we see peaks and valleys, and the squiggly line, or it could be called a fingerprint of that water, is unique to that water at that point in time. And these peaks and valleys are indicative of certain water quality parameters. You can see the peaks in this slide are indicative of total suspended matter, and the troughs or dips are indicative of chlorophyll, or the algae in the water, or phycocyanin related to the blue-green algae. We've gotten better at measuring water quality over time. The sensors have improved, and as you can see in this slide, going from the left to right, Landsat 7, 8, Sentinel-2, Sentinel-3, where once we had the potential, or could be called suitable, for measuring these water quality parameters, now we're out here at highly suitable. So we've gotten much better. A couple of just key points about satellite remote sensing for water quality. It's great because it's a snapshot in time. It's looking at, in our case, where we have a high density of lakes, what is the water quality of all these lakes at this moment? And we can do comparative studies to look at the water quality, spatial and temporal changes in water quality for a number of water bodies. It's affordable. All what I'm talking about here are freely accessible, open access imagery. Once we develop an algorithm, and we use this over a number of years with some of these legacy satellites, such as Landsat, we can start to look at changes and trends in water quality. We can more and more, because of the rapid improvement in how we process this data, we're getting near real-time data, and our accuracy continues to improve. On the downside is these are inland waters tend to be optically really complex water, and it's hard to tease out the signal of the different materials in the water. We can see a potential interference from the bottom. We don't want to see the bottom. We want to just see the water column. Clouds. we hate clouds. Clouds are our nemesis. We can't do anything if it's cloudy. Get a drone, I guess. We can't see sometimes dynamic changes in water quality. We heard about some extreme flooding events. If that happens during a cloudy period, where it's cloudy for a week, we're not going to get any imagery to support that effort. As I mentioned, limited number of water quality parameters, things that are generally optically active, but things like temperature we're also very good at. Calibration and validation, we still need on the ground, boots on the ground to help us do it. Just as I said that, we needed to optimize the algorithms for the different ranges of water, optical water types, we call them, or different regions. We needed for validating these algorithms over the lifetime of the satellite, and also just to fill in some gaps that the satellite coverage we don't have. I would say there's 4 reasons why we see this rapid advancement of satellite remote sensing for water quality. And how's my time? Eight minutes. Okay, thank you. The 4 factors which I would contribute to this rapid advancement: 1, new sensor technology. 2nd, big data, cloud processing, our ability, the memory, the power of some of our computers and cloud processing. Algorithm advancement, we're seeing a lot more, of course, with machine learning and AI tools to process our data, and education and capacity development, things like this workshop here. I'd be remiss not to mention some of the great work and some of the great scientists here in Central and South America that are doing work on water quality using satellite remote sensing. I just cited a few of the papers here. There's many more, and there's some excellent scientists doing work in this area. Entrance ramp to data products. So one of the problems a lot of people have, that they want to get at this information, but they don't even know where to start. And it is hard. It's every time I pick this up and start looking at where things are at, things change. This is a quickly evolving area. So I've broken it down into 3 general categories. One are web apps, portals, places you can go and click and point, and it'll tell you what water quality or satellite remote sensing information is available for there. And I'm going to be talking about this, of course, more on Saturday. Probably these first 2 we'll be talking on Saturday. Second of all, PC softwares. There's a couple softwares out there which are freely available. CDAS and the one that the ESA Snap tool, which is ESA supported, where you can process these imagery yourself. And third is cloud resources, which I won't talk about, but was mentioned in some of the lightning talks, things like Google Earth Engine, some of the programs that are out there, some of the Python scripts, which now can be used to get at this information. I just threw in a couple regional images that I just pulled up last week or processed, just to show you, one, maybe the range, the spatial range of which we work. Some of the imagery is quite wide and can help us look at water quality changes on a regional basis. Such as this top one, which includes central and the northern part of South America. And then we can zoom down. The second panel on the bottom here is a Sentinel-2 image of Lake Nicaragua. Many of you have probably recognized it. This is a true color image. This is what it looks like. And then we've processed it for chlorophyll, TSS, and CDOM. And you can see this is the lake here, the 2 volcanoes that are out in the middle of the lake. See, it's spewing a little vapor coming out there. But it, again, just showing some of the power of these tools. So I'm going to wrap it up there, but just put a plug in for Geo AquaWatch. I actually have some printouts here, just a one-page flyer on Geo AquaWatch. As it says here, our goal is to develop and build the global capacity and utility of Earth observations, water quality products, information to support the water resources management and decision makers around the world. So there's a number of folks that it's for the most part a best effort, volunteer effort, and there's folks right now for that probably 300 to 400 people are part of Geo AquaWatch. So I would urge you to engage and become part of Geo AquaWatch. Here's the link to their website, and I'll quit there, Nina. Thank you.
Thank you very much for an inspiring presentation. And if you would like to learn more about this, a quick announcement, we still have 2 available spots for the training that takes place on space technologies for water quality monitoring, Earth observation data for water quality monitoring, hosted by Steve. Please approach us in case you're interested in joining. And is there any question from the audience, either on site or online, that you'd like to ask now? We will have a discussion later on, but please feel free to ask a question related to the presentation now. Shanlong Lu, please.
My question is that for some local application, the method will be very easy to use because we can easily find some verification data. And then if we're using your systems to globally or large regionally, how to find this kind of verification data? Do you have some ideas or ways? Yeah.
So validation of some of these global products has been an issue, is still an issue. We wrote a proposal and was funded by NASA to run a validation workshop in Madison. I guess it's been almost 2 years ago now. But the big issue is, where do we find this data? Who pays for that data? There are a couple databases out there. Of course, CBAS is the NASA database, which if you get a NASA-funded project, you have to put your data in CBAS. So that's there, but a lot of that, of course, is open ocean or even coastal water. Nima Pavelon from NASA Goddard has put together what he's called the Gloria database. Again, that's more inland and coastal waters. And then the University of Stirling in Scotland has a database, Limnades, it's called, which is strictly inland waters, I believe, and has varying degrees of access depending on, you might have to apply to get access to it, depending on what the source is. You have to be granted permission to use it. But you're right, this is an ongoing and an issue. One of the things we've talked about, and we haven't written the report yet, one of the recommendations will be kind of the development of this global validation network, where people can, again, maybe through Geo AquaWatch, can come together and pool their resources for these more regional and global projects. Hope that answers your question. Anything else?
Are there any questions from the online participants? No? Okay. We'll have a chance for more discussion after the 3 presentations. And without further ado, I would like to introduce the next speaker, Mahesh Champany from the International Water Management Institute in Sri Lanka. Mahesh is a researcher at the Institute. He's an expert in water quality and hydrological modeling and holds a joint PhD from UNU Flores. That's the United Nations University Flux Analysis Considering Global Group, Considering Global Change Assessment Unit at the University of Dresden. And Mahesh will present remote sensing estimations of water quality dynamics in the Asian mega deltas. I'm curious to hear more about that. Mahesh, floor is yours.
Thank you, Nina, for that brief introduction. So just before I start, actually, I have to say, GeoAquaWatch, which Steve mentioned, he was the director and he recently stepped down, which is a community for water quality, dealing with remote sensing based water quality monitoring. And we are core group here. I mean, if you look at the water quality who is looking through remote sensing, there's a very limited number of people all around the world, the scientists. And it's always hard to sell to a stakeholder if you're measuring water quality through remote sensing. It's a tough thing. But Steve done some tremendous work through GeoAquaWatch. So great to that. And so my brief presentation will be on the remote sensing estimations of water quality dynamics in the Asian megadeltas. So I will take you from Costa Rica to Asia, basically Ganges and Mekong Delta regions. May I have the next slide, please?
Pointers.
Thank you. Great. So to briefly introduce what is Asian megadeltas and how the deltas are more important regions. If you look at any ecosystem, the fragility of the ecosystem or the volatile and how much anthropogenic pressures are going into the system. So that's defined by our human impacts and more recently in the last century, the climate change impacts. And if you look at the Holocene to Anthropocene and to the recent, we are more core into the Anthropocene, where we have the fresh, all the new ecosystems and everything is fine in the Holocene era and Anthropocene when we human era started. You can see slowly lots of resources are collapsing and the deltas are most vulnerable ecosystems where when a delta ecosystem collapsed, it's easy. The lots of millions of people who are dependent on this delta region will be directly impacted by the socioeconomic and livelihood sources. And so to analyze the Asian megadeltas, we developed a bigger framework of social hydrology and in that fit into that water quality part where salinity is a major thing where the people directly depends on the water resources, but salinity is a critical factor that influencing people to adopt the agriculture practices. So that's why water quality is a critical factor in this entire framework of social hydrology and how we deal with from water resources variability, quantity, quality to how the societal response happens and how this information goes into the sharing, how the stakeholder response happens, and also at the same time, the new adoption of the agriculture measures. And to briefly introduce you, we are initially planning to work on three Asian megadeltas, which is Ganges, which is Bangladesh and India, and Irrawaddy, which is Myanmar, and the Mekong Delta, which is Vietnam and Cambodia. But due to several reasons, we are not working in Irrawaddy majorly. So IMI is majorly working on Ganges and Mekong Delta regions. And if you look at the Asian megadeltas, they are more vulnerable to climate shocks and also anthropogenic impacts. They are highly intensively agriculture areas, and they are majorly rice-grown areas. And if you see it, so all of the area is like heavily rice-grown, and also from the last century, especially this has been intensified into double crop and triple crop also. And if you look at the salinity trends of the Ganges, in the top part where the Ganges Delta, where you can see the slow pockets, which showcasing the salinity is low. And if you, from the coast to the top, the salinity is year by year encroaching into the Delta region. And this is from the 100 years now, from the 50 years now, how it will be. It's a tough to measure, but there is climate projections and everything, continuous monitoring going on, how to mitigate this and take measures to control it. One is tidal effects and sea level rise and the climate change, and also huge anthropogenic pressures. And the Mekong Delta is also same. If you look at the salinity trends, it's also the similar from coast to the upstream. The salinity is encroaching year by year into the Delta region, where the lots of farmers depends on the rice irrigation for agriculture purposes, and they use this water for irrigation. but salinity is a factor that's limiting them. Sorry. So sorry. So salinity is a factor limiting them to adopt the new strategies and new rice varieties. And so in these two deltas, salinity has become a major factor to influencing the irrigation patterns and how farmers are adapting as a double crop or single crop. The Ganges Delta, which region, one of the polders we are working on, the farmers are heavily using the groundwater in the upstream of the polder, where in the downstream they cannot use. So this majorly because the accessibility of the groundwater to the local people. And if you look at the alluvial terrain of the deltas, there is three layers. One is the upper aquifer, which is highly saline, and the second aquifer, which is second aquifer, which is a little bit around 100 meters, and the third aquifer is deeper aquifer, which where the I already have one. So the third aquifer is the where deeper aquifer where the most people depend on for drinking purposes. And the salinity dynamics are heavily linked to the socioeconomics of the delta system. And if we want to do the remote sensing based stability estimations and using Sentinel-2 data and link this with the salinity and turbidity of both these delta regions, and in broad, develop integrated models to link water and salinity to design the agriculture system design in Asian megadeltas. If you if I speak loudly. So NDTI is a normalized differentiative turbidity index, where you can see the turbidity trends from the coast to the upper region. This is the Ganges Delta. And if you can see from the coast to the top, where the April is the dry season before the pre-monsoon, and in the upstream, especially where the high level turbidity, you can see it around 0.3 of NDTI. And whereas in August, which is a monsoon season, you can see the turbidity is drastically gone down. And this has a little bit variation when you compare to 2023, where the high turbidity values are observed in March, and whereas the September is the one where the low turbidity and after the monsoon season. So these trends are changing from year to year, depending on the rainfall patterns and everything. And so this map is briefly developed for the entire water bodies, but we have to mask it out to the only river bodies, then we can have a clear picture more. But if you look at the overall trend of the turbidity trends, especially the NDTI, and the monsoon has a very high impact. If you clearly see the trend from 2019 to 2023, so the turbidity drastically goes down when the monsoon season happens. And this is the season where the farmers are using either rainfall patterns or flooded rice through canal irrigation and everything. But when they go to the dry season, where the canal irrigation cannot be used also because of the high salinity trends in the surface water bodies. And if you look at this is a direct salinity data, and previously NDTI, there is a direct link and correlation. You can see the pattern of the graph is very similar at the same locations. And the flood salinity is where the tidal incursion happens. Ebb salinity is when the tidal is releasing it. And both times actually, the salinity is a dynamic factor impacting the monsoon crop, and there is a dry season crop. So to further go into that, we want to develop a salinity forecasting model where we want to link the turbidity and salinity together, how turbidity has a direct relationship with the salinity and how this can be plugged in together. So that's where we want to develop this salinity forecasting model for specific to your polder, and later include the remote sensing based estimations also into the system. Then we combine with the in-situ monitoring and we can develop a robust forecasting system. So this forecasting system will helpful for the farmers to estimate when is the good time to start the crop. And further bringing into the surface water where we're talking about the salinity monitoring and everything. So the groundwater is a tricky part where the people heavily depend on the groundwater as well, but always the accessibility and also which aquifer they want to tap into is also a critical issue. So that's where we want to combine the surface water and groundwater interaction modeling, where we initially we're developing for the polder system. So scale it up to in the next 3 years, if possible, to the entire delta system. So when we scale it up, so these remote sensing based measurements can be plugged into the model where we can do the seasonal patterns and estimate how entire delta system is drastically impacting, how we can develop different scenarios for the farmers, when to start the crop and when with the high water consumption and irrigation practices of the polder system and the Ganges Delta irrigation schemes in the Mekong Delta. So to conclude, actually, water pollution is a significant problem that influencing the cropping patterns and socioeconomic conditions, both in the Asian megadeltas. And high salinity in pre-monsoon or dry season affects cultivation in these deltas. Remote sensing based estimation providing critical insights into the seasonal patterns. But this is also a tricky part, actually, when we look into the remote sensing based estimations. They hold true for the most of the rivers, but some of the rivers, they don't give you any reciprocal, some good patterns. So that's where we have to do the in-situ monitoring and validate it more robustly and everything. So drawing the relationship between the turbidity, salinity, and density variations is very important. So that's where we are now, where we are linking the turbidity and salinity. And the other one is the density variations. So if you look at the GRACE data, GRACE is a satellite which you can monitor total water storage. So the GRACE gives you the density variations based on the gravity. And so in the deltas, especially the salinity variations will be very drastic and dynamic. So we want to see how the GRACE can help us to any differentiation with the salinity with respect to the seasons. But the problem with the GRACE data is for the entire Ganges Delta, we have only 350 pixels. And for entire Mekong Delta, we have only 135 pixels. So that's a critical thing. We need to see how, because there's a 300 square kilometer area that each pixel carries on. So how the density variations can map into these regions, how if you want to look at the entire delta system, how that can be bring in. And we are currently doing the in-situ monitoring of different parameters with water quality. Then we want to validate all our data sets, remote sensing based estimations with the turbidity and salinity. So overall, our aim is to do the water quality management system that can inform agriculture planning within these two delta regions, and how comprehensive understanding of interconnectedness factors can shape the functions in these Asian megadeltas. And because these are very fragile ecosystems, so that's why we want to bring in lots of stakeholders also. So we're working with several stakeholders within these two deltas, and they can inform immediately what the model outputs are, and they are also involved in co-developing these models. So thank you. Sorry for my.
Even when your voice is out, I think all of us have benefited from this presentation. And if there are any questions online or here in the room, please raise your hands. Or yes, please introduce yourself briefly and then ask your question.
Thank you. My name is Laura Venegas and I work for CATIA. This is a Center for Tropical Research and Education. Sorry to translate it in English. Well, my question is just to know about the scenario building that you put in your one of the last schematics. Do you consider to include climate change anomalies or other factors in order to build? I know that there is a lot of uncertainty, but there are products based on remote sensing and elaborated that could give some insights about the building of those scenarios, or if you already considered, maybe you can clarify. Thank you.
So in generally, to briefly introduce, IMI is a research for development organization. So we want to, generally for any hydrologist, they go and develop scenarios, what they think of. And normally I also used to do the same. But we reached out to the stakeholders. They're all involved in a workshop, and we're asking them, if we develop these models, what are the scenarios we want to include? So they gave us critical inputs. This happened in early this year. So which scenarios to develop? So we came up with the 4 scenarios, which is on the climate change impacts, of course, and how the anthropogenic impacts relate to the irrigation patterns, and also specific inputs, how the salinity dynamics with respect to either domestic water consumption or the irrigation water consumption, and also specific to the crops. The other one where rice is the major crop, but there's other cash crops also going on recently with the shifting from rice to the cash crops. So based on these major 4 scenarios, we want to inform stakeholders, different management strategies, what we can do with the hydrological modeling, combining remote sensing and in situ data.
Are there any other
question
Yes.
from the online audience. It says, greetings from Kenya. My name is Nancy. Thank you for your presentation. My question is, how often do you update the salinity data?
So currently for the remote sensing based estimation, we can get it for every monthly twice, mostly, but we are aggregating the monthly data now. But the in situ monitoring, we are doing it 3 months once in Ganges Delta and monthly in Mekong Delta. So this because of the logistic issues, nothing to do with the specific monitoring system.
We have another question from Shanglong Lu in the room.
Sorry, I forgot to introduce myself. I'm Shannon Wu from the Aerospace Information Research Institute of Chinese Academy of Sciences. My question is that I just saw that you're using the historical measured salinity data to get the background of the salinity of this kind of delta. And then you're using the measured or forecasting discharge to reverse or to forecast the future salinity. If the background of the salinity is changed, how to solve these problems?
So salinity is majorly impacted by the tidal incursions. So what we want to see if from the upstream, so the Ganges water coming from the very upstream where the India releases the water coming into the Ganges Delta. So when the discharge with respect to the seasonal trends of the discharge, how with respect to this discharge and the salinity is going on. And also there is a flood and ebb salinity where the subdaily pattern. So that's secondary. And the third one is the tidal incursion, where this subdaily of flood and ebb thing going on. So seasonal tidal incursion, how is this going on? So these 3 are very important to go into the salinity monitoring, but discharge is the critical one. So that's why we primarily concentrate on the discharge. How much is the discharge coming in from the upstream? Because if you look at the monsoon season, the discharge is very high. And based on that, the salinity is also low in the monsoon season. And if you look at the dry season, the discharge is very low. And at the same time, the salinity is very high. So we want to see how the discharge can influence the total forecasting system.
Is there one more question? If not, then we'll have a chance to ask more questions in the discussion later on. But I would like to move to our next speaker, who's using quite modern techniques for his research. And the presentation is on hyperspectral imaging and artificial intelligence for the detection and quantification of agrochemicals, such as chlorothalonil utilization in Carta O. Alexander Solis Quesada is going to be present, and he works at the Delta Lab at the Instituto Tecnológico de Costa Rica. Alexander is a technician and industrial maintenance in industrial maintenance, sorry, and an active student of mechatronics and engineering. He's also an active member of the investigation lab named Delta Lab. Alexander, the floor is yours.
Thank you very much. I'm very glad to be here and very honored. And I think that I'm the first Costa Rican presenting today. So first of all, I would like to welcome you all. I hope that you're enjoying this beautiful country, its beautiful people, and that you have a great stay. So yes, this presentation will be a little different from others because I'm bringing you a proposal on a project that is still on diapers. So we're going through some of the concepts that we have planned for this mission. Okay, so here's the content that we'll be covering today. First, we're going to start introducing you to a problematic that is very concerning in the presence of Costa Rican. And also, I'm going through some background research. Then we're going to talk about the mission objective, its timeline, and concept of operation. And we're going to finish talking a little bit about those key performance parameters or objectives that we want to achieve through this project. So Costa Rica is quite famous, and we are quite a little country. So it's mainly that fame. It's mainly because we are promoted as a green country, and I don't have any doubt that you have already seen it with your own eyes. Costa Rica is such a beautiful country. It's full of nature, and well, I'm very proud from being a Costa Rican and of all the work that we have made for this to be this way. And it comes to my mind talking about how we almost only depends on clean energy sources. Also about the whole environment conservation, but there's not only good news. And here in Costa Rica, we have a very concerning problem, and it's the use of agrochemicals, the abuse of agrochemicals. So it may be surprising for you to know that here in Costa Rica, we have drinkable water from the tap. That's something that's not common in all the countries. And this privilege, because I think that that's a privilege, it's on risk because water sources are being contaminated with agrochemicals. And the last UNDP reveals that Costa Rica is the #1 country in the world also in the use of agrochemicals. And the main concern comes when we start seeing what these agrochemicals can mean to health. And most of these substances are very dangerous for human consumption and also for other native species here in Costa Rica. And more recently, in a couple of years ago, chlorothalonil was banned legally here in Costa Rica. And it was because it was detected that it contaminated Asada, that is like the facility that distributes water here in Costa Rica. And this happens in Cartago. That's the province in which I live in. And okay, just to point something very important, the agrochemicals that are used on crops, they wash. And we today have heard about how water drains and goes through underground sources. And here in Costa Rica, the main source of drinkable water is underground water. So I'm going to talk a little bit about the background research that fundaments this project. First of all, we question ourselves, how are we detecting the presence of dangerous substances such as chlorothalonil? And the answer is that in Costa Rica, the main lab is ubicated in the Universidad de Costa Rica. And they take samples from superficial and also from subterranean water sources, and they test them. through hyperspectral samples. So this kind of test can also be made in soils, fruits, and vegetables, but this is out of the scope of the project. The important part here is that this testing requires a lot of time to really testify that water source has been contaminated. We need proofs of presence of agrochemicals throughout several years. And also, this test requires specialized personnel and specialized equipment that may rise its costs. So what are the alternatives? We are, yes, so we are considering hyperspectral imaging data because there has been some recent studies in Japan in crops and in products that has been successful, and that they say that it really is possible to identify the absorption spectrum of an specific agrochemical in a plant through this kind of images. And also, so if you're not like very specialized in hyperspectral imaging, they are like a photograph. So the difference is that a photograph is an array of numbers that normally contains the amount of red, blue, and green that there is in a single pixel. So in this case, these special cameras, hyperspectral cameras, they are the same. They are an array of pixels, but in each pixel, we have information about how much light there is being reflecting or absorbing in different wavelengths. Okay, so these images are highly dense when we're talking in terms of data. And there's where the artificial intelligence comes in. So when I tell you about artificial intelligence, I'm talking about a convolutional neural network, which is a network that has its own characteristics. We think that this is the best approach to the problem because these kind of networks, they can work with big inputs like an image. And they can be trained to identify patterns. And for example, there's a really known exercise when we are learning about artificial intelligence networks. There is a convolutional neural network that identifies from a picture what number is there written. So any of us writes different. We have our own handwriting, and the ability that the AI have to identify the patterns and the characteristics and to really generalize that problem and understanding that if I write a 2 different that you do, it's the same number. That's what we call deep learning. So we're trying to put these two technologies together. And this leads me to the objective. So what we want is to generate a tool that identifies the use of dangerous agrochemicals, such as chlorothalonil, through hyperspectral Earth imaging data. And we have to start with a viability study, and we're going to do it through drones. So we're going to equip drones with hyperspectral cameras, and we're start collecting a large amount of data because there's a relation between the amount of data AI needs for its training and the difficulty of the problem. So in this case, we have a lot of variability because we have different species, we have different kind of agrochemicals, and different linings in each photograph. So we need a really big amount of data. And then we're to our neural network for it to get trained. And afterwards, we're going to test the results by showing the artificial intelligence some pictures that it hasn't already seen in its training. And this will really give us a good image or how do you say it? Like a perception of what may be the precision that we are looking or that we are going to try to get with this tool. So the next step will be scaling it, scaling this work for it to work with satellite hyperspectral imaging. And this is very important because even though I'm from Cartago and we want to attack the problematic that there is in this province, and I'm sure that this problem it's present in all of our countries, and we have to really start taking care of the water. So through this application to satellites, we can start also monitoring the presence of dangerous substances in other countries and other regions. And well, here it comes like a difficult part, because when we escape from drones to satellites, there are a lot of variables that comes in and that we have to take in. Some were already mentioned, but for example, clouds and other meteorologist phenomena, it's very distorting to our measurements. And also the resolution may vary, and the amount of landscape that we are observing in each photograph may vary. So here is an important part of the work. It's to identify all the variables and take them on count. And evaluate the results that we're having with the software here on Earth with an AI trained on Earth. What we want is to deploy a real-time detection system on a satellite. So here is the concept of operation. What we want is to have a satellite in orbit that it counts with a hyperspectral camera, but it also has uploaded the software that we're going to develop. So in real time, it's going to take photographs and it's going to send reports constantly to Earth, telling us how much and what are the substances that it's detecting in the different landfills of crops. And here in the Earth, we can download that information, analyze it, and really to the decision makers and other stakeholders. Which are the goals that we're going to achieve? And this is like order in yes, like chronologically, what thing that it will be, and all of these steps will be recorded and document, and probably we're going to make a publication or two about each of these. So first of all, we need to start identifying the absorption spectrum of agrochemicals, starting with chlorothalonil, because even though it's being legally banned in Costa Rica, we suspect that it's still on use, or there are substances really similar to it still on use. So the idea is to identify these through hyperspectral imaging data. Then we need to see if it's viable to collect data through drones equipped with these special cameras. And the next step will be identifying the hyperparameters of the convolutional neural network. And this is very important. We need to optimize these hyperparameters because the computational resources that we have on satellite are really limited. So we need a really optimal software. Next up, we're going to train the convolutional neural network, and we're going to start testing how good it is at identifying the presence of agrochemicals and also the amount of them that there is. Afterwards, we're going to scale it to experiment with satellites. This is the most emotional part. And lastly, we're going to deploy a real-time satellite application for the detection of agrochemicals misuse, hopefully in making an application that is open for all the world to use. I'm already finishing, but I would like to mention that the idea is not to convert us in some kind of agrochemical police, but what we want is to raise concern and start like sending help, because in most of the cases the use of these substances is not because people want to do harm, but because they don't know the harm that they are doing. And thank you so much. And if you have any question or feedback, I will be very happy to hear it.
Thank you very much. I see we have a question. Please
Okay.
introduce yourself and ask the question.
I'm Sumaya Muhammad from Egyptian Space Agency. I'm actually a communication designer or system designer. My question is about how you classify the type of chemicals according to the wavelengths of each hyperspectral.
Okay, so mainly it's through its absorption spectrum. It's like a fingerprint for each substance, and it may vary between each species of crop. So that's why it's part of the experiment or the project to start identifying which is spectral, the absorption spectrum of that agrochemical in each crop in a special, well, like especially. And also, well, no, that would be.
So this means that each chemical type have a different footprint than the others.
Yes, correct. And the absorption spectrum of a substance will depend only on, well, this the surface in which it is put, but also the chemical composition, and that you can cover that with anything.
Okay, thank you.
Oh, thank you very much, Alexander, for an interesting presentation. You said that it's possible to do some scaling also. And for within a country, I think there would be less amount of conflicts or resistance. But if it was at a transboundary level between countries, then where do you see this particular technology being applied with particularly relating to the differences in terms of methodology, in terms of thresholds or the ways that you apply that method, for looking at different chemicals and categorize that would differ for each country, and whether you would have some kind of a agreement or disagreement on that.
Yes, a very important part of this project will be how big and strong of a network we can do with entities that represent all the interests of the society. So we need to have people that represent farmers' interests, and also in public relations. And transparency is a very important part of this project, and it's something that it isn't always like that in water quality topics. Are going to document every single step for it, that if any country want to approach us and will help us, and also replicate what we are doing, they can do it, because what we want is not just the application, but the results and the impact that it will have on farming culture.
There's another question. Please go ahead.
Thank you. The idea, I think it's interesting, but I was just wondering, how can you capture a very tiny particle that is at the same time moving and at the same time could be like together with other particles? If in the lab is difficult, I wonder to do that by a drone or whatever, that it may have some kind of resolution. I mean, the idea seems interesting, but I don't know how feasible that is.
Yes, that's why the viability study is very important, and it may reveal that the precision that we have isn't that big, because you're in the truth here. It's going to be very difficult, but maybe it can give us hints to where to look with laboratory tests. So, for example, it will help us to go and test some areas that may be contaminated, and we can't really tell the amount of contamination, but we know that there's something that we have to look at that place, and that's the idea.
Just to follow up, is okay, Nina? To his remarks, because I'm a little bit confused myself. So were you going to start with a given matrix like water? I mean, like DI water, and add given concentrations to do some kind of systematic build up some kind of calibration, or at least see if it works? Or is this to put on plant leaves, soil? And again, the concentrations, I would think, in sub microgram per liter, are you going to be able to detect that with your sensors? I'm just wondering how far down the road you've gone and where it's shown promise.
Well, as I was telling you at the beginning, the project is still in diapers, and there's a lot that we don't really know accurately. But yes, the idea that we have for the beginning of the project is to start on plant leaves of certain species. So, for example, in Cartago, the crops that we mainly have are potatoes, onions, and stuff like that. So we're going to start with some test fields in which we can, well, see the amount of, or how the spectrum of absorption is, how it varies when we apply these kind of chemicals. And also we need to take on count, for example, the irrigation of the land of the farm, also rain, for example. There are a lot of variables that we have to take in count, and that we are going to try to really consider. But yes, it is still like a very beautiful thing when you just think about it. But when you start digging up, there problems start to appear. But we in academy love problems, no?
Thank you so much. I also have a follow-up question, but then I would like to open the floor for questions on all presentations again, because we have time for a discussion in this session. But my follow-up question is, generally speaking, when we do water quality assessment with hyperspectral imaging, how well do we detect the presence of specific agrochemicals in the water bodies, not on the plants necessarily? Can we do that, and how far can we do that? And maybe Mahesh Champani can also speak a little bit about how his experience with the rice crops was in the Asian mega deltas. Do you have any experiments on that?
Sorry, I didn't get that question, Gail.
So have you had any experiences using hyperspectral imaging in the Asian mega deltas? Because you mentioned rice crops are present in the area. Have you focused mainly on salinity sensors?
So I'm focusing on salinity. My colleague, who is not here today, so he is doing rice mapping of the deltas. So they're using that, yeah.
They're using it?
Yeah.
And do they have experiences with the different substances, like the different agrochemicals
No.
affecting the water? Okay.
I'm wondering how this is possible, because agrochemicals is a typical chemical, but even tough to measure in a lab, actually. because you have to go through lots of species differentiation, and the chemical species differentiation. So wondering, I mean, if it's results are come up, just please let us know.
Thank you. Thank you.
So in the research that we made before presenting this project in the university, we saw that it's already being done in a small amounts. So for example, there are some certifications for farms that requires that they pass as clean of agrochemicals, and on small samples in a laboratory, it's possible to identify the agrochemical through hyperspectral imaging. So the scaling it to more further photograph is the part that I'm not sure if it could be made.
Thank you very much for your presentation and good luck with the research. I would like to open the discussion now to all the presenters.
To say something about the hyperspectral camera image.
Okay.
Our colleague in Egypt, they work in using the image of hyperspectral camera for climate change to decide or to draw the map for concentration of CO2. So by the way, they can do for chemical because they see what's the observation of the wavelengths for each type of chemicals, and they can draw the map for that concentration. That's all.
Thank you very much. Are there any questions for Stephen Greb on his presentation, or for Mahesh Champani on his presentation on the Asian megadeltas? Do we have any questions from the online participants? Okay. I will have a few. So in terms of in situ data availability, Stephen, you mentioned a few portals that can be accessed to retrieve samples at certain conditions. Where do we stand with the different parameters that we want to observe in terms of the availability of in situ data, and for which regions are they generally available and not available? Where are the gaps when it comes to in situ data, and what can be done to improve the situation?
Yeah, well, we touch on that just a little bit at the end of my talk. I think there is a lot of gaps. Where to begin, I don't know. I would say we probably have the most coverage in places like the US and in Europe. I think, when we're talking about doing CalVal work with satellite remote sensing, we like to have some optical information collected, not just the end water quality parameters, such as chlorophyll or suspended solids, but information about the absorption properties of the water or the backscattering of the water, and those are even rare. There's small groups or research or investigators around the world that are using that kind of equipment. At the validation meeting last year, we talked about, could we raise funds for a community set of equipment, like a traveling set somewhere where these instruments could be shipped around, or people could be trained on them, because you're not just going to ship them off to somebody who's never seen it before, but because they do take some mentoring or getting used to them. But so there's options like that have been discussed. We are going to come out with a publication, or would be submitted soon, which will have a list of recommendations from this workshop. So I'm hoping in there there'll be more and broader idea of what and where we need to go. We have some sense of who is doing what now, in some sense of the gaps, but not all. And we're hoping, again, as more sensors and sophistication is improved, and some of these algorithms, that we won't need the validation work as much as we do now. But I mean, that's a ways off, and I wouldn't want to comment more on that.
I do understand that there's also a difference in the time that a water sample needs to be brought to the lab for different parameters. So in some areas of the world, we see issues with labs being in the vicinity of the areas where the samples are being taken. Is that correct? And how do you think this problem could be addressed in order to get more samples done? I think the Atomic Energy Agency, they have a laboratory network that they launched at the UN Water Conference in 2023, hosted in New York. And I think maybe there is potential. They're using it for other purposes, but I think it'd be great if the space community could get in touch and cooperate there.
That's a good, I mean, I didn't know that, but we'd definitely be willing to talk more about that, or what its capabilities are, or what the needs of our community would be. But yeah, there's definitely timing issues and getting samples to the lab, and just getting access to the water bodies. Being able to get out on the water is problematic in some areas. I mean, boats, logistics, it's hard.
I see a question from Mandira.
Well, thank you, Stephen, for your presentation. I think one of the issues that you highlighted was the use of citizen science to collect data and for validation and calibration. So that it probably adds to the in situ data, a little different, I guess. So what are some of the challenges that has been faced in terms of the using this particular method of collecting data, because this involves quite a lot of capacity building of the locals as well as awareness, and how far there has been a challenge in terms of the accuracy of the samples that are being collected versus what actually is being measured.
Right. First of all, I just say we love our citizen science monitoring people. They're very good. And I think I mentioned that they're really vigilant about getting out there on the days we ask them to. We give them a little calendar which shows which days the flyover is of Landsat 8, Sentinel 2, and then they mark it on their calendar in the kitchen, and then they go out on the lake and collect the sample when the satellite's coming over, provided it's not thunderstorms or something like that. There is a learning period. We do screen these people. There's trainings that they're required to take, and they do have to go out and do a Secchi disc, if you will, and we check it based on what we have. But we have found most of them to be very vigilant and conscientious about what they're doing. A lot of them are retired engineers or scientists or teachers, and they've done very well. We actually had kind of a Secchi disc contest between some of the local water resources staff and the citizen science people, and their variability and their accuracy was actually better than the water resources staff for where we'd sampled. So yeah, I have a fair trust in citizen science, but we don't ask them too much. We don't, and they're not doing a lot of things which would require a lot of training and background. It's basic things like water temperature, Secchi disc, clarity, things like that.
If somebody wanted to replicate the citizen science experiment, let's say in their region, how much effort goes into scheduling, like making the appointments of the satellite overflight, like these plans for what kind of area, and how long do you need to train them before they can go into the field?
Yeah, Well, one, I'm not, that's not my role in this, so it's not a thing that I have that much experience with, but I mean, I think it doesn't take long to do the training, but again, they have to read the materials. I think they might even take a little test. If they're interviewed. I can't remember what your other part of that question was.
How much time do you use for training them? Like how long do they have to undergo training before they're ready to go to the field?
Right. I would say we would run these trainings a couple times a year, and it's just open to the public for them to come. We work not just with the citizens, but what we call our extension agency, or agency which does a lot of work with the public, and they have someone who's dedicated to doing this training. We don't do the training, but we actually have materials, printed materials for handouts that we use. So those materials are available.
Okay, thank you so much. Are there any other questions? Are there questions on the other presentation of the Asian mega deltas, maybe online or in the room? We heard a lot about salinity intrusion into the river, depending on the monsoon season, crop planning for farmers, informed decision making. If not, let me ask you, Mahesh, what are the next steps in your research in that area? What are the pressing challenges that need to be addressed?
So in general, we want to develop this salinity model, so where we can inform local communities and the farmers when is the high salinity going to be increased. Salinity values are low, so they can start the cropping season with respect to rice or any other crops. So that's the next steps. So where we want to full-scale model development and giving it to the local stakeholders, and also, yeah, that's my slide.
Okay, thank you.
And related to the in situ data, actually, there is lots of.
Can you increase the volume a little bit?
So there might be a lot of stations already there in North America and Europe, but there is a lot of in situ data not available in majority of Asia and majorly in Africa. But AMCO, which is the African Council of Ministers for Water, so they are taking initiatives to how to develop this in situ, develop the local stakeholders, doing the capacity building to them, and then taking more samples. Yeah.
Thank you. Okay, then I would say we can wrap up the session. We've heard a lot about monitoring various water quality parameters in water bodies by use of Earth observation data such as chlorophyll, turbidity, salinity. We've also heard about the use of GRACE data to assess relations between turbidity, salinity, and density variations, and the involvement of stakeholders to define better decision-making tools for crop decisions. And then we've heard about a project idea, I would say, or project plan on how to monitor agrochemicals that are affecting our health by using hyperspectral images. And if we get any results of your research at some point, Alexander, I think, please share them with us. With that said, I would like to thank the speakers, and we'll continue with the theme of water quality, both in our next session. But I would also like to announce now that over the break, please screen the lightning talks that we didn't do before for the online presenters. And all of us, maybe we can use these 10 minutes. Unfortunately, it's behind the coffee desk, but We have lightning talks on water quality that are both linked from the program online, but also accessible if you scan the QR codes on the poster cards outside. And with that said, I wish you a nice break, and we will return at 4 o'clock for the next session. Thank you very much. Please, can you put on the lightning talks for the online ones?
Kariba is on the northern part of Zimbabwe. It is a crucial tourism hub with visitors attracted by the largest. Hello, my name is Tando. My name is Tando Mati. I'm going to be talking about the use of open cloud platforms as accessible tools which policymakers in developing nations can use to make informed decisions. I'm going to use an example down here in Zimbabwe, where we'll be measuring the turbidity in Lake Kariba. So Kariba is on the northern part of Zimbabwe. It is a crucial tourism hub with visitors attracted by the largest man-made lake in Africa. The lake is a crucial source of economic and social activity for both Zimbabwe, and I'm going to be talking about the use of open cloud platforms as accessible tools which policymakers in developing nations can use to make informed decisions. I'm going to use an example down here in Zimbabwe, where we'll be measuring the turbidity in Lake Kariba. So Kariba is on the northern part of Zimbabwe. It is a crucial tourism hub with visitors attracted by the largest man-made lake in Africa. The lake is a crucial source of economic and social activity for both Zimbabwe and for Zambia. And in most cases, there are multiple stakeholders which are involved in the management of this large water resource. but for the most part, they lack the financial, technical, and human resources in order to use space-based data for evidence-based decision making. So in Zimbabwe, the problem that we face the most is the lack of financing and sufficient technical infrastructure for data processing. I'm going to be demonstrating how Digital Earth Africa, a platform which provides open access to several magnificent tools that you can use for this data. It only goes to show how easy it has become to access this data and how even low resource setup policy organizations can use this data for their own decision making. So we start off by measuring water extent by loading the water observation from space suite of tools. It uses Landsat 8 and Landsat 9. So we do this so that we separate water pixels that relate to water from those that relate to land, because when we're measuring turbidity, we want to make sure that we are measuring it on water bodies only. So turbidity, we measure it using the NDTI, which is an index that we find by, in terms of bands, the difference between the red and the green band as a ratio of their total. So lower turbidity means the water is clearer, and higher turbidity means the water is a bit dirty. So you will find that on the edges of the lake, which is closer to the land, you find more turbid water, which is quite expected. For the sake of argument, we're going to assume that it is because of the depth of the water. It's shallower. So Digital Earth Africa also provides an easy way to create animations so that it's easy to tell the story visually to non-technical policymakers. So we can now look at this initial assumption that we made earlier. When we look at the graph on the bottom, you can see that both small and large water bodies are exhibiting the same characteristics when it comes to turbidity. Therefore, we can expound that assumption that we had made earlier. And then when you look at the graph on the top, which we easily generated as well in Digital Earth Africa, you can see that the seasons with higher rainfall are also coinciding with seasons with higher turbidity. Therefore, upon further investigation, we can conclude that the two are related. This information is useful, particularly in the data-driven age, where in modern society it has become practically pointless for you not to use data for your decision-making processes. In Zimbabwe here, specifically with Kariba, it affects the fishing industry, the tourism industry, and the public health industry, both of which are related to the health compared to the quality of water for both people and animals, which also in turn affects economic decisions that will be made on in tourism, for example, electricity generation, for example, and as well as decisions to do with fishing activity, the type of equipment used, the type of chemicals used perhaps, and all those are decisions that can be made based on the data that we have acquired here. So thank you very much for listening to my presentation. I look forward to
Hello, everyone. Thank you very much for this opportunity. My name is Mongeni Tamara Manda. I'm an undergrad student at Chino University of Technology here in Zimbabwe. I'm the main author of this research on monitoring water quality of Lake Chivero in Zimbabwe using Digital Earth Africa. And Kenneth Mubeyo from Digital Earth Africa is the co-author. This research was conducted in southwest of Harare, here in Zimbabwe, on a Ramsar wetland named Lake Chivero, which is the main water supply for Harare, which is being used for purposes of irrigation, domestic use, and habitats for birds in Zimbabwe. However, over these years, this lake has been facing pollution, siltation, and invasion of water hyacinth because of urban growth, land use, land cover changes, and climate change. As such, this delicate ecosystem, seasonal changes in these water levels can have huge impact on the water being provided to the people. In this study, Digital Earth Africa was used to study the changes in water extent and quality over time with comparison with the CHIPS data. In this study, a normalized different water index was utilized to provide the water index for 6 years from January 2017 to December 2023. And in comparison with the rainfall data generated by CHIPS, it indicated high levels of drought in October 2020 and floods in early year of 2021 because of tropical cyclones. We can see the variations of this graph showing floods in the early years of 2021 and by 27 January to February 2021, variations of floods. After calculating the water extent, water quality was then estimated using the normalized different chlorophyll index, which informed the presence of algae in this water body in Lake Chivero. And these high values of NDCI, we can see by these graphs, they indicated the presence of chlorophyll. And by performing these relevant calculations across these 6 years of data, we can see the variations in chlorophyll level, which indicated the periods of drought in January 2018, October 2019, and November 2020. These two graphs, they show the water quality and the variations of chlorophyll level. In conclusion, these results are very important and they're crucial for inputs for governments or agencies such as Ministry of Lands in Zimbabwe, which are responsible for managing and monitoring this Lake Chivero site, which is the vital nesting and breeding ground for birds. So by mapping these correlations between these findings and birds counts in Zimbabwe, efforts can be made to protect these important habitats into the future as Zimbabwe is continuing to battle with the effects of a little rainfall on its ecosystem. And this is also important to inform sustainable development goals, leaving no one behind. Thank you very much for this opportunity to showcase the study, the research that I did with the help of Kenneth Mubeyo from Digital Earth Africa. Thank you very much for helping me to do this study using the Digital Earth Africa platform on this wetland, which is very important to monitor the water quality of many water bodies in the world so that people, they know the type of water they are drinking to avoid and mitigate problems or health problems in the world and achieve the sustainable development goals. Thank you very much for this opportunity. Thank you.
Greetings. This is Engineer Aish Yusuf Al Mahmoud, a space data analyst from Bahrain's National Space Science Agency. Our discussion today will revolve around spatiotemporal analysis of water quality parameters in the Arabian Gulf. We'll look at how researching the water quality indicators in the Arabian Gulf may help with conservation and management efforts now. Using the Google Earth Engine platform, this research study examined the water quality parameters, specifically turbidity, chlorophyll concentration, and total suspended solids in the Arabian Gulf region from January 2022 to March 2024. We examined spatiotemporal changes in these characteristics using advanced geospatial methods, offering a thorough insights of the dynamics of the aquatic environment in the area. The research covers the Arabian Gulf with a 251,000 square kilometer area indicates higher intensity of scattered light caused by substances like silt, clay, and algae. Pollutants can negatively impact ecosystems, and evaluated levels of fine particles are often indicators of these increases. Throughout our study, we delved into the second parameter, the chlorophyll concentration. Chlorophyll serves as a crucial indicator of both biophysical health and biological productivity within water bodies. Chlorophyll levels in aquatic environments indicate increased nutrient inputs from wastewater or agricultural runoff, leading to pollution and harmful algal blooms. Effective water management is crucial for aquatic life and fish sustainability. One metric used to evaluate the quality of water is total suspended solids. It can be caused by biotic or abiotic factors, runoff, erosion, farming practices, wastewater discharge, or events of nature like algal blooms. Evaluated total suspended solids can cause sedimentation, degrade aquatic environments, smooth their benthic creatures, and affect water quality by decreasing oxygen concentration and increasing turbidity. Through regular and economical measurements of water quality indicators, we can create an organized monitoring system that covers vast areas, including inaccessible places. This board approach makes evidence-based decisions possible, enabling stakeholders to take major steps for the protection of our aquatic ecosystems. Additionally, through the use of remote sensing technology, we may create early warning systems that safeguard public health and reduce environmental dangers. We can achieve a great deal of progress toward the Sustainable Development Goals, especially Goal 6, Goal 14, and Goal 15 with all of our efforts. Let's work together to create a future for our valuable aquatic ecosystems that is sustainable. Thank you for joining us in this important endeavor to understand and protect the Arabian Gulf's aquatic ecosystem as we work towards a better future for our planet and all its people.
Hello everyone, I am Bassam Rafat, a geodata scientist in Earth Observation Department, Egyptian Space Agency. Today we will have a look of how using remote sensing data for water quality assessment. Our study case on the North Lakes of Egypt. As we know that the traditional method used for water quality assessment takes long time and effort. For example, for the measurement of the quality of the water, we need first to collect samples, then send these samples to the laboratory, which take time and effort. But nowadays, with the power of remote sensing, we can analyze satellite imagery and obtain information related to everything, such as water quality. In our work, we aim to provide an effective water management analysis for the North Egypt lakes and addressing the challenges posed by harmful algae blooms. In this study, we focusing on use Sentinel-2 L2A data alongside other sources of data to classify and analyze North Lakes of Egypt. As we can see, the next flow chart represents the steps for our study. First, we start with download Sentinel-2 L2A data, which is atmospheric corrected data. We choose 4 dates from 2021 to 2024. Then we start to choose our bands or that we're gonna use in analysis. We choose a red band, green band, and near infrared band. Then we stack all these bands to one TIFF image using Python code. After that, as our region of interest covered by different tiles, we merge all needed tiles using Python code. Then we mask the generated tile with the shape file of each lake, so we can apply analysis on each lake separately using Python code. After that, we start our analysis by computing different indices for monitoring the water quality. First one is the chlorophyll vegetation index, which can be used as indicator for measure the algae exist in water. For computing CHL, we use near-infrared band combined with red band and green band. The next figure showing for you represents the chlorophyll for 3 lakes, Etko, Porolus, and Manzala, in different dates, from 2021 to 2024, and show how the CHL changes per year. Second index is the turbidity normalized index that can be used for measure the water clarity, and it's related to the amount of suspended matter represented in the water. Clear water corresponds to lower turbidity value, while murky or cloud water will have a higher turbidity value. Also, the figures represent the different values of turbidity in different years for the 3 lakes of Egypt, Etko and Porolus and Manzala. The next table shows our result, which is the area of algae and the area of high turbidity regions in Manzala Lake for years from 2021 to 2024. As you can see that the area related to algae and turbidity decreased in Manzala Lake by 2024. The next table shows the area of algae and the area of high turbidity regions in Etko Lake. As we can see that both turbidity and algae area decreased by 2024 too. Also for Porolus Lake, both turbidity with high values and algae decreased by 2024. In conclusion, the integration of water quality indices with Sentinel-2 L2A data offers a promising alternative to traditional methods for measuring water quality. This approach approach not only enhances monitoring capabilities but also facilitates more informed decision making regarding water resource management. Our next work and our future work is utilizing MasterSet 2 data and AI techniques to further enhance our understanding of water quality dynamics. Thanks.
As well as Tapioca. I'm going to be presenting, sharing with you my research on assessing the sewage water systems, the effects of the sewage water systems in Zimbabwe and the world at large. So the sewage, the effects of sewage has been a problem that's been very ubiquitous in most African states, even in Europe as well. But where do we get the sewage that is affecting most of our communities and also our environment at large? The industry, the households, the commercial industry. All of these industries are contributing to the increase of sewage, of untreated sewage, which is leading to the leakages and ending up polluting our environment. So what do we do in order to curb and also to monitor and also to assess the effects of sewage systems around the world? With the increase of urban population in the world, recently it's been over 50%, meaning that in the next 20 years, the number will increase, thereby increasing the volumes of the sewage in the country and also in the world at large. My case study, I was able to calculate NDVI by downloading the images from the platform USGS, which gave me the opportunity to assess the vegetation state of the river near around the river banks. All of these vectors, all of these tasks were able to be completed for me to be able to bring out the final report, which I was able to see the effects of the sewage leakages it had been causing, it had been harming the environment for over past 20 years. Due to the increase of the population in Masingo City, the local council were unable to solve the sewage leakages problem because the sewage system were meant for a lower population. Through GIS, I was able to manage and also monitor the effects of the sewage water systems in Shagashe River. And this is the end of my presentation. I hope you find you well.
In this video, we're going to be making a USB Type-C touchscreen monitor that has a super unique look to it as it's made out of brass. Now, brass has been chosen for this build as it allows it to be flexible functionality. So as you can see, it's quite an exciting project, so let's get building it. The first thing that's needed for this project is obviously the LCD panel itself. If on a tight budget, it's worth noting that these can be pulled from old or
If folks want to take their seat, we'll get started in a minute. Okay, I think we'll go ahead and get started. I hope everybody has a lot of energy and ready to finish this day strong. We have one last session to get through, and I think it may be a short one, since I think we have a couple of no-shows here, or I think at this point we're down to 2 speakers for this session, so we'll see how it goes. Maybe they'll still show. So this is the session T2, S2, Space Technology and Data for Water Quality Monitoring. Our first speaker today, the title is Uncertainties While Classifying Cyanobacterial and Microalgae Blooms. Francisco Namina from CANE. Francisco is a physicist student who has been working on the CANE on ocean color and water quality topics for the last 8 years. Currently is focusing on uncertainties of water quality indicators provided by remotely sensed data. So Francisco.
Sorry about you. Well, hello. My name is Francisco. I'm from CONA in Argentina. And my idea for... That's me. I will do 2 jokes. That was the first one. The idea for today is to speak a little bit about hyperspectral data and how we can use it to classify cyanobacteria and algae blooms. This is an image for San Roque Reservoir in Córdoba, Argentina, taken by the Prisma satellite by the ASI, the Italian Space Agency. And it's a nice satellite. It has several bands, especially in the visible. We have 66 bands that are less than 12 nanometers width. And what we've been trying to do is to say, okay, I got this hyperspectral data for my lake. I want to identify what kind of bloom I'm having on the lake. So what I say is, okay, I will treat this as an spectral and mixing problem. I will have some water, some bloom. When my satellite measures, it's all averaged over that zone. But then I want to say, okay, my sample is a linear combination of the different algae I can have in my reservoir. And I will work backwards to get the fraction of each spectra, the fraction of each species of cyanobacteria or algae, and the concentration. Yes, I want to go backwards and recuperate something that has to do with my mix in reality and not what my satellite measured. And to do this, what we do is we try to minimize a distance function. There are several to do this. You got the Euclidean distance that it's here, but you also got the spectral angle, the n-stray. You got tons of things you can minimize to get your values that, okay, this is my linear combination. And when you do that, you get a result. So it was going to be short. You get, okay, I got that most of the lake has no cyanobacteria. It has Cryptophyta, that is another species. And then in the middle, where I had the green part, I got cyanobacteria. This is what we expected for the lake because we know it. We know that it has blooms every once in a while that are pretty big with concentrations over 500 milligrams per cubic meter of chlorophyll. So it's good. But then it comes a problem here is, okay, but your satellite has a problem. The measurement from your satellite is not perfect. Your atmospheric correction algorithm is not perfect. Your spectra to do the unmixing are not perfect. So you got uncertainties all over the place. And I like this quote from Juan Herrera. He's an Argentinian physicist that when he spoke about measuring, he said that if you measure several times, you will have several results, especially if you drink wine between one measure and the next. I didn't drink anything here, but there is this thing, okay, if the satellite comes again and measures again, will I have the same result? Can I trust this result? And this is where the travel starts. This is what I wanted to really talk about. That is, okay, how can I say something about my degree of trust with these results? And how can I quantify the errors I'm committing in this spectral and mixing from the satellite, from the spectra in the field, from everything, yes? To do this, we did some simulations. First, we started with generating water reflectances using hydrolyte to get members. Then we got the top of the atmosphere reflectance using 6S to get what the satellite would have measured. Then using the Acolyte software, we did the atmospheric corrections and we knew our input, and now we can try to get our output. We do the unmixing, yes. So we can compare, okay, I put this input into my system, half cyanobacteria, half not cyanobacteria, and I got this output into my system. And I can say, okay, I got more noise in the satellite. I got 0.5%, 1%, 2% of error at top of the atmosphere. And I got this atmospheric correction algorithm. And then I say, okay, I got this error in the fraction of each one. To do this, we did some hypothesis testing and used the Neyman-Bell construct to try to get these values. And here I'm missing something. Okay, you have to imagine something here that you have two distributions. One will be over here. That is the distribution for, okay, my result is right. What I put for input is what I got for output. And the other one is over here that is not right. And using this, you can do hypothesis testing and say, okay, if I want 66%, 68% of my data to be in my confidence interval, then this is my threshold. If I want 95, this is my threshold. If I want 97, this is my threshold for the Euclidean distance that we are talking about. We can calculate this for different uncertainties for the top of the atmosphere reflectance. And then we have a criteria to say, okay, if you did the unmixing and the distance, the Euclidean distance is less than this value, you can say the unmixing is good. And if you did the unmixing and the Euclidean distance is greater than this value, don't trust this. This is not good. And you can say it with different confidence levels. And you can also say here, you have to use your imagination. It will be better here. You can define the confidence interval for the fraction that you have. So if you measure with this uncorrected algorithm here, and your value was 0.4 for the fraction of cyanobacteria, then your plus minus is 0.15. Yes, you are in that interval. And if you correct it a little bit more, you can do the same here and say, okay, my interval is plus minus 0.5. That's the kind of things we are trying to do. You got a pixel, you get uncertainty, you get how confident you are in that result. And we can now do that. Yes, this was the classification. Yes, that we got here for the cyanobacteria and here for no cyanobacteria. And you can see that if we put the cutoff values that we got before, it's not good. Yes, with a confidence level of 1 sigma, nothing in the leg was well classified. So this is really nice, but the truth is you don't have to trust this. If you go with a confidence level of 2 sigma, then okay, this part of the leg seems good, but the rest of the leg is not good. Yes, you have to keep working. And if you go to 3 sigma and you are quite of stretching it, you can say, okay, you got more of the leg, but this is not among your spectra. Your mixing that you did is not right, even though you got a result that looks right. Yes. So you can do the same to get the uncertainty for everything. And this is the kind of problems that I believe sometimes we hide under the rug, that we don't talk about, that we got the classification, it's good, but this classification could have been done for the leg with a road and trace, and you will have had a result. And it's not a good result, because when you go, you do the statistics, you do everything, per pixel, you can say, okay, this is not good, this is not good, this is not good. How do we improve this? We can. And to improve this, the first thing we need is more in situ data. This kind of a mixing algorithm are really sensible to the end members that you have. If you have trace and roads, you will do one mixing and it will be bad. But if you have the specific species that you have in your leg, then you will get a lot of better result. The problem is then you have to measure in your leg absorption coefficient, backscattering coefficient, everything. And it's for one leg. You want to do it for everyone. So we can do this. We can perform these in situ measurements, but we have to be careful. We have to get the in situ data for our results to really match what we expect, even though the initial result might look good. Yes, this is everything I wanted to talk about. I work in this group at CONAE, at Instituto Gulich. They do a lot of water quality parameters, data. You got people working in snow, in algae blooms, in hyperspectral, in lots of stuff. So any question, you can ask it. And thank you.
Questions from the floor? Yes, sir.
Amjad Ali from Sparko, Pakistan. My question is more toward the methodology which you have adopted in this particular study. My question is targeted toward the selection of the technique which you have used. You used Euclidean distance. But do you have any particular reason for not using the new technique like convolution neural network or the random forest technique, because they are also giving promising results in complex data context?
The idea here was I use Euclidean distance because I thought everyone will know it. So it's easier to imagine that you're minimizing the distance. We tried two more. We tried a spectral angle mapper, and we tried NS3, that it's a mix of spectral distance and spectral angle mapper. In the future, we want to try more techniques, but our main focus is not on the unmixing. A lot of people are doing that and are doing it quite right, but on how you can generate uncertainties for the mixing with the data you have from your satellite. So we could have done random forest, and we would have had results, and then the same analysis would have to be done. In random forest, I guess you will also get a result. And always the idea is, okay, now go back and say something about this result, about the statistics of this.
Other questions?
Distinguido, ¿cuál es la diferencia entre una criptobacteria y una cianobacteria?
What is the difference between a cryptobacteria and a normal cyanobacteria?
The question is, what's the difference between cyanobacteria and cryptophytes? In this work, I only used two species of phytoplankton. We are really interested in cyanobacteria because they are toxic and they are present in our lake. And Sand Rocket Reservoir is the drinking source for Córdoba City that has 2 million inhabitants. So it's important to say, okay, you can use this water or you have to treat it in another way, and to see how it evolves in time. For this work, we choose Cryptophyta because it's present in the lake and it gives the best results. But you could do it with tons of species, and each lake, each reservoir will have their unique phytoplankton flora, and you'll have to do it for your lake or reservoir or whatever.
Yeah.
Well, thank you for your presentation. This is Mandira. Yeah, I was wondering whether there's any kind of threshold or limitation in terms of the size of the lake or the water body that can detect these, bacterias.
Okay, the limitation is more on the spatial part of this. Currently, that I know of, you have 3 hyperspectral sensors. You have Prisma from ASI, you have NMAP from the German Space Agency. They are both 30-meter resolution, so a lake of Sand Roque Lake is 2 kilometers by 5 kilometers, and you can do it there. Then in the last few months, you have Prisma. Prisma is from the NASA. It has a 1 kilometer resolution. The main difference between Prisma and NMAP and PACE, is that PACE is 1 kilometer, but it's functional. You get data every 2 days. Prisma and NMAP, you have to ask for it, and you have a temporal resolution of 1 month. So it's not so good data. It's good for research, and they have done tons of things. But if you want to implement something that runs every day, you will have to go to PACE, and PACE is 1 kilometer resolution. So for a Sand Roque Lake, it wouldn't be so good. So the satellite PACE is 1 kilometer resolution. So your reservoir, your lake will have to be 5 by 5, 10 by 10 kilometers. It will have to be larger. In the next few years, there are going to be tons of new hyperspectral satellites. I know NASA has 1 in the making. I know ESA has 2. So there will be more data to do this, but currently this is our limitations.
Yes, thank you. The PACE mission was just launched in February, and NASA right now is releasing the funding for the research that goes into PACE for, in particular, water quality. Over the next 2 years, it's going to be $9 million spent just on the research to work on the algorithm development, et cetera. Just a quick follow-up. Again, you mentioned there was 2 species or genera that you were using here. Did you know a priori that's what was in the lake? And if it was a soup, of 10 species, how would that complexity be handled, or was it just a multivariate equation?
Okay, for the lake, what we know is that in general, you have one or the other dominant. When you have blooms, you always have some of the other species. So maybe you have, I don't know, 5 milligrams per cubic meter of Cryptophyta, but then you have 200, 300 milligrams per cubic meter of Cyanophyta. And then it's like one is always dominating over the others. We didn't do this, but the Córdoba Hydrological Department did some measurements separating species in the microscope, and in general you have like 80% of one species and the other 20% is divided among 10, 20 species different in the lake.
Okay, anything else from the floor or online? If not, we'll move on. Thank you very much. So the second one listed here, I don't think has showed up online, and we don't have a presentation for the talk from Sri Lanka. So we'll move on to, and I'm not sure, is David Zamora here? Oh, there he is. Okay, great. So our next speaker, David Zamora, is a civil engineer with experience in evaluating hydroclimatological effects related to land use and land cover transformations with the eco-hydrological approach, pollutants detection through continuous measurement technologies, and machine learning methods, water and soil resource management. And today he's going to talk about separate land use, land cover, and hydroclimatic effects on cyanobacterial harmful algal blooms in Weha Lake. Is that right? Okay, thank you.
Thank you so much, and apologize for my voice. I try to do. My name is David Zamora. I am civil engineer. I work with SEI, Stockholm Environment Institute. Today I go to show some results about the algal blooms in Weha Lake. This is the content of my presentation. We had some context about what happened in Weha Lake related with different use of land and different hydroclimatic effects, materials and methods related with the input information, related with in situ data and image from remote sensing. And after I try to explain cause and effects related with algal blooms, preliminary results, and some conclusions about it. This is Weha Lake. This is Weha Lake. It's a transboundary basin located between Guatemala, Honduras, and El Salvador. It has several subbasins like Ostura River, Anguilla River, Lempa Alto River, and the other ones like Usmapa and Wajon. Yeah, is related with dynamics in Weha Lake. So you can find the main streams that discharge the water inside of this lake. This basin has several crops, different a kind of different quantity of populations in these basins. And nowadays, we have several causes or sources can affect the water quality in this lake. But in several media, you can find different news that say you what happened with chlorophylla, yeah, and different algal blooms. And for example, here you can see the news about the relation with volcano activity, with different feature activity and gold mine event, and maybe used on other kind of media like Facebook to communicate what happened with the lake, and finally produce the effects on the ecosystem, like several deaths of fish in this lake. So in materials and methods, we use the spectrometry to try to identify different dynamics in terms of water quality. But when I think in water and sump, I remember the Pink Floyd album Music, yeah, and 3 songs for this album. The first is Time, the second is Money, and Are You Color Like? That is very related with dynamics of we have in this lake, in the first kind of time, try to represent different dynamics of land use that can affect by runoff with a lot of different kind of pollutant. In the case, for example, of crop, you can find different nutrients like nitrogen and phosphorus that can introduce elements or pollutants to increase the algal bloom presence. But we have a problem with money, because in tropical area, even in Latin America, we don't have a lot of information for in situ data, for example, chlorophyll, TSS, COD, BOD. And these elements can to say what happened with the water quality dynamics. So you try to identify with these samples different behavior of the water quality, but the limitation of the number of measurements are high. Are hard with respect with another kind of information, and with ability to identify the cause and effect. So we need to another kind of alternative source of information. In this case, we use the non-invasive measurements like satellite of drones to identify different elements in the spectra are related with the presence of different kind of parameters of water quality, and after that try to identify what happened around the lake. So in the materials, you can see here 2 missions from Landsat 7 and Landsat 8. Their availability data, in situ data in blue color. We have a lot of information, but we have a limitation in terms of parameters. We can find, in this case, the blue line represent all chlorophyll data, but we don't have all data related with nutrients like phosphorus and nitrogen that are very related with algal blooms. And in this map, you can see the different points that are monitoring by different environmental authorities in Honduras, El Salvador, and Guatemala. And we collect this information from this time period from 2006, for 2023. Yeah, but we select just this time period because we have a more relation between image from the satellite to the samples. We don't have a specific information for the image to related with in situ data, so it's a high limitations for our analysis. And after that, this is the algorithm. It's very simple. You can use linear data. We have lake. We use the satellite image, and after that, you relate different bands for the image to calibrate the linear regression, and after that to elaborate the spatial distribution of the chlorophyll A. And after that, we try to identify what happened with different kind of patterns of precipitation in the year. And are there some significant changes in the precipitation that can affect or increase the presence of chlorophyll A in the lake? And in this case, we use the standard precipitation index to try to identify some tendency in this variable using the Mankendal test. So the question is, could the precipitation be decreasing, and with this increase the concentration of some pollutants in the Ouija Lake? So to explore this question, we start to identify the main crops in this basin, that we can see the 30% of area are related with agriculture, and we can find the principal crops, kind of crops in this area. You can see, for example, in the upper Lempa River, related with coffee and other kinds for melon or even for some grains. Yeah, and we try to identify what happened in the time. So I explain more about it after. But here we have the main data from in situ samples and measurements for some in situ proof. Here we can find the chlorophyll A, turbidity, and blue-green alga. Yeah, and you can find some correlation between these variables to identify what happened in terms of the increase or the decrease is the concentration of these parameters. And we can split the information into elements, into season, in dry season and wet season, to start to calibrate different kind of regression models, linear regression models, to combine different kinds of bands in the spectra. And after that, you get the correlation, the coefficient of termination. Yeah, in this case, this algorithm was very interesting because gives a inverse relation between the between the band rate with the chlorophyll A. So we evaluate another parameters, but in this case we use this equation. So with this equation, well, in this case is for wet period. In this case, we have a lot of clouds, and we can have a very poor correlations and coefficient of determination. So we select, in this case, this equation to represent the dynamics of chlorophyll in both seasons. And this is the result. Here you can see 2006 to 2023. And here for dry period, we can find here a good results in terms of performance to represent the chlorophyll, but we can find several problems in other moments, because we don't have a match between a satellite image with the chlorophyll data in situ, and worse in the wet period. I know it's about results, but the indices of spectral indices help you to identify what happened around the Ouija Lake. And with this equation, we represent in the space what happened in each moment of the year, and related with precipitation. We can find, for example, in December, the high moment to presence of chlorophyll. We have in this moment less water and decrease the level in the lake. So it's most probably to increase the nutrient in the column of water. So, but in the case of a moment with more precipitation, we have more runoff and stream flow to inside the lake. So can you reduce the presence of chlorophyll, for example, in May? We estimate for another for each sample, yeah, and establish the dynamics around the GR. But after that, we start to evaluate the trends of precipitation. Here you can see the monthly demand of water. Here the monthly precipitation of the GR, and you can start to see here what happened in terms of trends of SPI. Yeah, in this case, we analyzed just the trend with significant trend. That means the Mankendal was less than the alpha value, so the p-value is less than 0.05. And just in this area, you can find the precipitation are increased, and you can identify this is here in the lake, and several of this area that gives a lot of runoff and to the lake is increasing nowadays. And the other evaluation is evaluate the trend of vegetative production using NDVI to 2000 to 2020. Here you can see the main kind of crops like coffee, like grains, like vegetables, and tomato and melon. These crops are present, increase the production. In this case, the more interesting is here the melon and the coffee. Coffee is a very important crop because it uses a lot of nutrients. Yeah, and for in the river Ostua, arrive a lot of nutrients. Nowadays, we can try to connect the precipitation, the spectral indices, and the vegetative production to identify what is the main reason or are several reasons to algal blooms in the Ouija Lake. So, for conclusions, high heterogeneity of water quality information limits the spatialization of chlorophylla. The information that we can find from different environmental authorities was very different in terms of quantity and spatial representation, but it's helpful to identify areas of lake that where monitoring should be prioritized. Yeah, because more than the exact value, you give us some recommendation for environmental authorities to give more money to improve the monitoring. Give us some ideas to explore other drivers around the lake, such water quality, the algal bloom, and the ecosystems. For example, in the case of fishery, is need to explore more in a deeper way, because they have a lot of feature area around the lake. And although the reduction of precipitation is a hydroclimatic factor, was not observed, mainly supply basin. In other side, you can find more precipitation and increase the runoff. So in that case, you can find the reduce of concentration of nutrients. And some ideas exist to use the more drivers to analyze the HAP events, but transboundary condition and scale information are important limitation. Thank you so much.
Thank you, David. Questions from the floor?
That's great presentation. I love it. I have a doubt when you use Landsat 8 data, which atmospheric correction algorithm were you applying? Were you using level 2 data from the NASA, or were you applying another algorithm?
I applied NASA algorithm. Yeah, this case was the in this moment that was used. Yeah, in this case, we have a plans to use another kind of satellite missions like Sentinel, but we don't have enough time to do that. But I hope in the next semester to start to explore this satellite. Okay, thank you so much.
Follow-up question.
Okay.
Not so fast. No, I just, God, I forgot what I was going to ask you. So I noticed the precipitation, there was quite a bit, but then in the last couple of years, like it had dropped and then come back up. And, so maybe it's not just an overall linear increase, but there's a lot of variability there. And I would think there's like a lag in what the lake sees, like maybe algae in this lake are responding to inputs from, say, a year ago or something. Like it's not necessarily cause and effect. Like there could be some latency or delay. I don't know, just what your thoughts are on that.
Okay. In the case of Ouija Lake, yeah, I know the precipitation in that case I did show that is increased. No, but we need to explore more about what is the main or several variables that can affect the alga blooms. Yeah. In this case, can you repeat the question? Sorry, I can do it.
So just trying to look at cause and effect or relationships between precipitation and increase or changes in water quality. The lake can act as a buffer sometimes, and the changes you might not see it in the lake till the following year. Does that make sense or no? But maybe not. I don't.
Yeah, in the case of precipitation, we try to identify these elements are a part of input to increase the alga blooms. Yeah, but maybe the natural process in the lake respond to another kind of variables. For example, the crops around the area, and in a same time, those elements are increase the presence of alga. And another maybe is the regulation. For example, downstream of the lake, you can find a dam, so it's another element to affect. So there are co-variability of elements to affect the water quality in this lake. So in this condition, we try to identify some elements to give recommendation and improve the making decision from the environmental authorities. How deep it is? 2 to 30 meters. It's a shallow.
Thank you. If there's no other questions, we'll move on. Our last speaker of the day, the title is Risk Management Tool for Water Utilities. It's Natalia Rodriguez Alfaro. Is that correct? Close? Of Casa de Agua in Costa Rica. Natalia is an industrial engineer who has dedicated the last years of her career to projects related to strengthening the management and resilience of rural water utilities in Costa Rica.
Well, good afternoon, everyone. We have had an amazing day full of extraordinary presentations. And for me, it's a privilege to be here presenting you on the critical issue, risk management, water risk management. I'm going to present you a risk management tool especially designed for rural water utilities in Costa Rica. We are looking for empower these community organizations to manage risk management in a better way. Well, first of all, I will present you about the context in which this tool emerged, also the methodology that we choose for designing this tool. I'm sorry, I'm hearing myself in Spanish and I'm like, also, what is the tool, exactly the tool, that HIRA tool, and how we use the scientific geospatial information for risk mitigation, and show you some results about the HIRA and the uses that we have today. So first of all, we are in Costa Rica. We know that we have a multi-threat territory. We have climate change. We go from rainfall scarcity to extreme hydrometeorological events, even more frequent and more intense. Also, we have technosmy, seismicity, volcanism, the contamination of our fields with agrochemicals that Alexander exposed a few minutes ago. And we are in the middle of a region that had experienced several events from these tropical storms and hurricanes. We have the Hurricane Otto in 2016. We also have Nate in 2017. And now we are facing the Niño, that for us is up to 35% less of rainfall in some regions. We have an abusive land use for agriculture. And now all these are risks that the rural water utilities must face. What are our rural water utilities? Named ASADAs. Well, there are rural organizations that manage a significant part of our water supply. We are talking about 30% of the water population is provided by these ASADAs. We have around 1,200 ASADAs, but these ASADAs are very different between them. We have some that serve up to 6,000 subscribers, so a robust ASADA, but there are others that are smaller than with 100 and 300 to 300 subscribers. These are led by neighbors that go around and serve the community with water. And this was a challenge because we needed to design a robust tool that really solve the risk management problem that we have, but that can be applied for any ASADA. So for this, we got an interinstitutional project with all these institutions, led especially with the IIA, that is our national water institution, and also the UNDP. And we were the consultancy that had to solve this problem that we had. So for this, we needed a framework to put all these institutions together, and we decided to use the Sendai framework. This is disaster reduction framework as a global agreement adopted from the United Nations states to guide actions on disaster reduction. It has 4 priorities: understanding risk, strengthening disaster governance. We are talking about ASADA, so we needed them to feel empowered in how to battle this disaster risk, investing in disaster reduction, and also enhancing disaster preparedness for effective response. But the thing that we like it the most of this framework is that they promote risk identification based on local knowledge and also scientific expertise. And so what we did is to design a HIRA that is a tool that has the methodology, a simple Excel file where you can guide the ASADA with the methodology, and also a guide for developing comprehensive risk management plan in ASADAS. This HIRA allows the ASADAS the identifications, evaluation, prioritization, and management of the disaster risk within their system and services. We have 6 modules. The first one is the characterization of the system. That is basically, come ASADAS, let's look at a map of your system. What do you have? What do you have near? Let's see what are your risks. Also, we have a questionnaire of the vulnerability analysis, where we can see the gaps that they need to work with. Also, the threat analysis in the territory, the risk assessment and prioritization, and at the end, we get a risk management plan so they can improve year after year in their risk management for the water utilities. Today, I would like to expose about how the geospatial information help us in these 2 modules, characterization of the system and threat analysis in the territory. So remember that the Sendai framework tells us that you have to use the local knowledge, right? So we asked the ASADAS that please, let's build our map, because some of them didn't have it. Was the maybe one person that worked for 20 years in the SAT and knows everything about it, but we didn't have it, a document that explained us. So we began with this. And this, can I point here? Yes, these labels, they can identify which risk do they have if they have, for example, cows near the water supply. So it is a risk. What level of risk it represents? A low, medium, or a high risk. So in a simple way, we managed to get that information from the local knowledge. But we had to include the scientific information. So for that, we had a methodology that was built by the Master in Science, Maria Jose Molina, and the engineer Luis Diego Monge, here present, that create a methodology for generating risk index, which incorporate the necessary scientific information, but in a simple way, enough for any ASADA. So that risk base was based in a level of exposure of a subwater basin for the different threats. We have, let me go. We have landslide, drought, volcanoes eruption, fires, anthropogenic threats. All that information can be given to the ASADA to build and make decisions. So the way they did it is by measuring the level of exposure or the subwater basin, because every ASADA need to know what's about their water basin. So comparing the unit of measurement using a fishnet with sizes of 250 meters, so they can identify the hexagons exposed to each threat relative to the number of hexagons in the watershed. So the hexagons exposed are understood as the footprint of the mapped threat shape pile. This here is the last area of a study that we did last year. Every single point, blue point, is a water supply for different ASADAs, and the yellow limits are at a different sub-basin. So we needed to include all the threats. What we did is, for example, precipitation. We divided in each fishnet, and so we can understood that as a level of exposure for each subbasin. So this information was translated to a simple index from 1 to 4, so the asadas can get a number of level of exposure, as simple as that. So this is an example of the drought indicator, but we also did it for the seismic acceleration, for the anthropogenic exposure, and all the threats that we needed to evaluate. Imagine this asada, the asada Sabanilla de Costa, that knows a little bit of how this works, but then there's a tool that give you the level of index, of risk index for each of these streets. All of these streets, I got a number and a level that is can be low, high, too high, so I can take decisions from it. And also I can get a map, a simple Google Maps, in Google Earth, I mean, where I can identify my water supplies. And if I have, for example, a landfill that is threatening me, my water supply. Also, I can go to a better level of exposure and to see, for example, the agriculture that is affecting also my water supplies. All this was translated to decision making, to actions, corrective actions, so the asadas can improve year after year in their risk management for the water supplies. We also had the analysis, the vulnerability analysis that gave us specific corrective actions for each vulnerability, sanitary, operative, management, infrastructure. Also, all the threat analysis that includes, for example, the economic estimation of potential impact. That's what's included in the tool. So for that, they can take decisions about, is this impact risky enough to take decisions to invest in it, or I can handle it if it comes to me. So at the end, we got some products, the map, the risk map, the comprehensive risk assessment, and the prioritization of actions measures. We got also the action map, the action plan for risk management, including the corrective, preventive, the emergency response, and building continuity. And here in the preventive plan, I may mention that we use some plans of climate change adaptive measures. That is a new, more recently added to the tool. And also a self-assessment result report for water quality seals. Today, the HIRA is accepted as a valid risk management by the national institutions. This was designed by the national institution in Costa Rica that the AIA, but now it's accepted, for example, for the local governments, also for the health ministry, and all the others that come to the asadas and ask, okay, asada, give me your risk management plan, and they don't have a way to do it, So this is a solution for them. It's widely used by many asadas now. Also, is a case of study for students in their thesis and undergraduate thesis, and is projected by the idea to be developed into the web-based tool for applications in other countries. So this is the presentation that I have for you today. Thank you very much. I hope you enjoyed.
Thank you. It was really interesting. My question goes a bit in line with, so one big part of the HIRA, as you explained, is the Excel spreadsheet, which makes it pretty simple for them to follow and fill up. The question goes more on this GIS process that goes parallel to some of the analysis, and how is it expected, maybe, or planned in some way, the capacity building so that some of these things can also be done internally by the ASAs, and not to have someone externally coming and always having to do to assist them with that process.
Exactly.
And yeah, the
Thank you.
challenge that
Thank you.
represents.
Good question. Actually, well, in the tool, they got the index as a number, so they can go and see, well, for that row, I have an index of 4. So I will make some measures for some corrective measure for that. But more than that, we aim the asadas to work together, because it's not the same that I work for my little asada that work as a group of all the watershed. So we aim them to, actually, there is a part of the HIRA that says, okay, your neighbors of asadas are these ones. Please work together so you can solve the bigger problems as a group. So in that case is what we propose in the tool. But also there are other methods that are coming up to, especially for the emergencies preparedness, and how they can work in case of an emergency. For example, they share resources. Okay, I have some my human resources, I can give it to you so you can have it for your emergency, and we work together. It's a very good, we had very good experiences about that. Yes.
My question is again about the methodology. You have used the hexagonal shapes. Isn't it too old technique? And also you may feel more trouble with using the satellite data with it. So would it not be better to go for a grid, like equal grid, square shape? Then it would be more easy for you even to use further more compatible satellite data with it. What is your opinion?
Okay, I will ask them for that. But I think that there is well, I will not answer.
Okay, now what's handled. Okay, the idea of the hexagon is because of its geometric properties. It has the ability to better adapt to the different morphologies of that we're trying to study. So as you know, the hexagon is the geometric figure that can encompass the biggest area without the minimum diameter. And when you translate that into a map, it gives you like a better resolution. Yet it poses some challenges, because if you're working with satellite data, which has the pixels are square. So, but what we try to do is like to work with a statistical average for every hexagon. So yeah, it's something that we need to keep working. Of course, this tool is hoping to improvements, but so far it's been a great tool for different communities, and hopefully, if not us, other people will continue to work and continue to improve the methodology. Now that I have the microphone, I will also like to take the opportunity to once again invite you. Tomorrow we're having the field trip, in which we will be visiting one specific asada in the Valley of Orosi. They have implemented here, so you will have the chance to see how the local communities use these tools in order to improve their water management. And also, it's a pretty beautiful place, so you can get to see a little bit of Costa Rica during your visit here. So hopefully tomorrow will be a very successful and very fruitful field trip where we can all learn and also see a little bit of Costa Rica.
Thank you. Great presentation. I'm just wondering, is there any threshold values to raise the risk and to the communities?
And any pressure values?
Yeah. to inform actually you are of high risk, you should take some measures to control the risk or mitigate the risk.
Well, in terms of water management, each area has different threats. For example, in Cartago, the place that we were mentioned by Alexander, they have a big problem about quality of water quality. And the way that they have to solve that problem is different for them than for other areas in the countries. But the good practices tell us that one of the biggest resources that we have in water management is the community, the associativity from asada to asada. Now we are reinforcing asadas, not just to talk about and be ready to help, but to build an official organization of asadas so they can get, for example, more resources from the state to share with them. And I think that's the better way to solve risk management. I don't know if I answered your question or not.
Thank you. I have a question related to the 4 risk levels that are, as I understood, integrated in an Excel. Does that mean that's a static information that is like based on a general assessment that was done? And how can, for instance, water quality threats be then communicated, because the situation might change depending on the activities upstream? I think the web tool you mentioned would be a great extension, but I think that links also to the previous question, and maybe.
Yeah, the idea of the index is to provide a starting point for these communities to start the assessment. The HIRA tool has a lot of resources, a lot of information that the communities they research and they put that information in. The idea of having this index is like give them like a framework, like a guideline, so they don't start from scratch. So they have like some starting point, like, okay, this is a place that where we have risk of flood or drought or etc. But then after that, the tool is filled with information from the community because they are the ones that know their territory, and they are constantly updating it. So the index is like the starting point, but then the more crucial information is updated by the same Asara on a regular basis. Okay.
Sorry. Shouldn't be asking so many questions here and give the floor to others, but are there any institutions in the country that are feeding information into this? Because I think this could be very powerful if you partner up with water and sanitation agencies and environmental agencies to feed information that can be communicated to the asadas then, and that can benefit from the activities of the asadas. Is this something that has been explored? And yeah.
Well, actually, it is a limitation that is an Excel tool, that because it is static, and this index has to be updated in a, I don't know, I think that it is like every 5 or 4 years has to be updated. But there are some organizations that are interested in the methodology, but to apply them in their fields. What you are proposing is actually a very good option. So this index can be, for example, imagine that we have our web application now, and they can they can have the inputs in that application. So we can have, in that case, updated information. to get using for the asadas. I don't know if I'm explaining, maybe tomorrow we will understand it better, but the asadas are a group of neighbors that fight for the community and the water resources. So this tool and the information, the scientific information given to them, and if it is updated, will be an amazing change for their risk management.
Was there any resistance to acceptance of these risk tools from the ASADA? Do they think we know our watershed, we know more than you know? And
Well, actually, as the start point is, please give us your information. You know everything about your asada. We need to document your local knowledge. So in that point, we gain their trust for telling something. And the scientific information is more as a thank you. I needed this. They are amazed by the maps that they can draw and see all the information and all the layers that they can put. For example, okay, I want to know my I don't know, seismicity layer. Boom, I put it in my map, and I see, okay, no, my water supply is in a risk or not. That is not just a simple thing to imagine for ASADA. So if they are not, they accept it with open arms, actually, but they have a limit of capacity to, even if it is a simple Excel tool, sometimes it's difficult for them to operate it.
Me parece bien interesante. Sorry, it was very interesting. The asadas, the boundaries of the asadas are the boundaries of a watershed, right? The geographical boundaries of a watershed. And what about the people who manages those asadas? Do they have certain level of instruction? I mean, some basic technical level of instruction, or are very diverse? For example, this asada has people with certain level of instruction, but the other no.
Well, in some cases, there are asadas that share the same watershed because they're more like small political organizations that are built from the town. Neighbors from the town built the aqueduct, and then they began an asada. So there are very different levels of capabilities. For that, the AIA is inviting the asada to get a manager. The managers are the ones that level all the asadas in the same way, so they can implement these kind of tools. And in that case, there are our aliados. Yeah. So I don't know if that answered your question or not. Exactly. As I mentioned before, there are asadas that are like big companies with 6,000 subscribers. They're like bigger than many of the other asadas and work very good. They have their building and their cars and their tractors, that kind of asadas. There and others that have like, I don't know, 100 subscribers, and that's it. And they have to pay for the fontanero. I don't know how to say it in English. And they have to pay the rent and pay the, that's very hard for them. So this tool may help us get to a better level of management that maybe is not available for them in a simple way. Yes. Well, thank you very much.
So I think I'll go ahead and wrap this up or close this session. I want to thank Francisco, David, Natalia for their talks today. As I was listening to all three, I was again trying to rack my brain over what's a common thread between these three talks, because they're all fairly diverse or different talks. But I think in some ways they all discussed the uncertainties we have, or the uncertainties in our measurements, be it the amount of cyanobacteria or the relationships between watershed and water quality, or in this case, risk assessment, how we're trying to get better at, understanding the risk and with the ultimate goal of, we want a safer world. We are interested in ecosystem and human health, and we're hoping these tools will help in that respect. So with that, again, let's give a round of applause to all of our afternoon speakers. And I think I'll turn it over to Nina. Is that right?
Thank you very much. Thank you for interesting contributions throughout the day on various topics, from groundwater monitoring to drought and floods, mainly floods and drought, sorry, and then water quality monitoring. It's been a very diverse day in terms of the thematic areas that were covered, and we look forward to a social dinner together. Everyone who would like to join will be picked up by the bus, and we'll wait here for the bus so we don't have to stand outside. Is it here? Okay, the bus is here. We can see the bus. So let's go. Everyone who would like to join is welcome. And once the bus is filled up with the funded participants, if we don't have any spots left, then I invite the others to join us at Jardín Lolita at the market. The address you can find online. You see the name of the venue on the website. And tomorrow we have our field trip. So if you want to join and you're not at the Radisson Hotel, please come to the Radisson Hotel at 7 in the morning. That's when we depart. Ideally, you're there a little bit earlier. It's an early departure. Bring some clothes to change if you feel uncomfortable with your field trip cloth at the conference venue. But we're not going to judge you if you show up in the field trip cloth, and we will just discuss in that. Jonathan? Just some logistic information. Can we leave things on the bus during the field trip and it's safe? Yes? Okay, so in case you want to bring your backpack. For all those who are not joining us for the field trip, we will be back for lunch here and then continue with the afternoon sessions. And if you have any questions, let us know. And I would like to thank the online participants as well. Tomorrow, we will start for you with the lightning talks from 1 a.m. We will screen the lightning talks while we're having lunch at 1 p.m. Costa Rica time. Thank you, Mandira. And then we will screen the sessions in the afternoon for you, for the online participants. Again, if you have any questions on any of the sessions that you couldn't raise, you can use the form. And I wish you a nice evening and good night if you're overseas and joining us from there. Thank you.
Recording stopped.